that we're doing. I want to start it with discussing the exercise sheet. I don't know if you saw it like on the website. I put up an exercise sheet. Maybe you had some time to look at it, but we will discuss it now so that you see like some examples of how to apply what we learned about quantum information theory to some interesting protocols and interesting examples. And then in the second part of the session, I would like to talk about entropies again, and this time about quantum entropies, because we introduced them in the classical setting, but haven't talked about the quantum generalization yet, and some interesting consequences of like looking at the quantum version of entropies. Okay, so to start with the exercise sheet, I put it up here. Again, you can also find it on the website if you want to see it there. It's two exercises. The first one is about unambiguous state discrimination. So the question is, how well can I distinguish quantum states? If someone just like hands me a quantum system and says, okay, this is one of a number of states, it could be in either one of them, how well can you distinguish them by measuring? And the general setting is, that we're looking at here, like you have a set of n orthogonal states, and if I have such a set of orthogonal states, I can always come up with a measurement that distinguishes them perfectly. That's the first case, like we discussed in the last lecture about what a measurement in a basis is. Like I take the basis and I construct these measurement operators. And if I have such a measurement, then I can distinguish all the states in the set perfectly, actually. See? What you have to take into account is that not only do you have to take the measurement operators for all the individual states, but in case this is just a set of orthogonal states and not a full basis, you have to add another operator, which is just 1 minus all of the other operators, so that your set of all operators sums to the identity, which was one of the properties that we needed for a measurement. In case you already have a basis you're starting with, then this would just be 0 and you don't need to add this M0 operator. Yes?
I take the question, do you like record it? So
yeah, yes. Oh, yeah, okay.
It's done, okay.
Thanks for thinking of that. Okay, so now we have such these measurement operators starting from these orthogonal sets. The first thing that I want to show is that if I have such a set of measurement operators, then if I measure the state psi I, so one of the states in this basis, then the probability of getting the outcome I is 1. So if I measure a state of the basis in the basis, I will always get the corresponding outcome with probability 1. Okay. Do you remember how we calculate these probabilities of getting an outcome? So we start with like this state and have these measurement operators. Yes?
It's a Born rule.
Yes. So, to know the probability of getting outcome I. And here I'm only talking about pure states. So you take the state that you have, the state that you're measuring, and sandwich the measurement operator corresponding to the outcome you're interested in, which would be n I in our case, and psi I again on the outside. And then if we just plug in the measurement operator ni, which is also psi I, then we have all these scalar products of psi I here, and since these are orthogonal states, I actually should have said they are supposed to be orthonormal states also with norm 1. It means the scalar product of them within themselves is equal to 1. Okay, so that shows, like if I try to distinguish states from the set of orthogonal states, then with this measurement I can do it perfectly. Okay. Now we go to a different case where the set of states we want to distinguish is not orthogonal anymore. So now our new set of states that we're interested in is plus and 0. So two qubit states which are not orthogonal to each other. And I want to find out how well can I say, like how well can I guess which state I got when someone hands me a quantum system in one of these states. Okay, so the naive thing to do would be just like take one of those bases and just measure in the bases, so either in the 0, 1 basis or in the plus minus basis. We want to see how well can we actually guess the state in case we choose one of these bases. For example, like we choose the measurement in the computation basis. That means we have two measurement operators. So that means we have two possible outcomes, and we have to decide, okay, like each of those possible outcomes is supposed to correspond to one guess. So I have to say, okay, if the outcome is 1, we guess that the original state that we handed was 0. If the outcome is 1, then we guess that the original state was plus. These are my two possibilities. Okay, so now I'm interested in how likely is it that I make a mistake if I use this strategy. So we want to calculate like these error probabilities P. Just the, how did I find it? Probability that we guess 0, but the state was plus. That means the probability that the outcome of my measurement is 0, but the state was actually plus. In that case, you would make a mistake. And the other error probability is when the outcome is 1. So we guess plus, but the state was actually 0. And of course, I want to keep these probabilities as low as possible in order to never make a mistake when guessing the quantum state someone handed to me. How do I calculate these? Well, again with our rule for calculating probabilities for measurement outcomes, so the Born rule. You can see this probability of getting an outcome 0 when the state was plus means the state and the outside is plus. And then we need to put in the measurement operator for the corresponding outcome. That was the M0. This. And if you so if you plug in the measurement operator, this is what you get, and then you would have to like calculate the scalar product between plus and 0. And if you do that, you see that it is 1 over square root of 2. Remember, you could express plus as 1 over square root of 2 of the plus state plus the 1 state. And then you calculate that, and this is your value of the scalar product, and the same for this one. So you get 1/2 here. So the probability of wrongly claiming that the state was 0 is 1/2. And then for this one, you like do the same the analysis calculation. So the state is 0, but the measurement operator corresponding to outcome 1 and 1. This. And now 0 and 1 are orthogonal quantum state. So this is 0. This you never wrongly claim that you got outcome plus. That one, you never make a mistake in that case. But in 50% of the cases, when you say your state was 0, you would actually be wrong. So it means this strategy of just measuring the state in the computational basis, like, gives you the correct outcome in some cases, but you also make a lot of mistakes. Okay. But so far, we have only looked at what happens if you measure in a basis. But in the lecture, we also saw, okay, we can do more general measurements, namely POVM, so positive operator value measures. And they are more flexible because we don't necessarily need a basis to measure in. we can come up with something more creative. And that's the next example in the exercise. Now we just construct a PWM measurement that has 3 measurement operators. Okay. So like these 3 and 0 and 1 and 2. And the first thing that you're supposed to show is that this is actually a PWM, so this is a valid measurement. And to show that, what properties do I have to show?
All operators are positive. They all sum to the identity.
Mm-hmm. And there was a third one.
Hermeticity is assumed since we say it's positive, implies that the summation is a requirement.
No, not necessarily.
No, it is actually. Is it not?
No.
No, positivity is defined more generally.
Yeah, I mean, you can have a positive, like for example, you can have a positive definite matrix that's not symmetric.
No, but in a complex Hilbert space, I think the two are equivalent.
Really?
I'll look it up actually, I'll do it.
Yeah, okay, I'm not sure.
But yes, okay.
So what we need is x. We need to be Hermitian, positive, and complete, so sum to the identity. That they sum to the identity is pretty obvious from the construction because the last one is constructed as the identity minus the other two. So that one is very quick. I don't want to go through the calculation of the other ones in detail now. Like you can just build the look at the complex transpose version of these operators and quickly see that they're Hermitian. Yes, and then positivity you can show when they're Hermitian and they have positive eigenvalues, then it's also positive. So this is just like a quick calculation of these operators. What's more interesting is what we can do with these operators now. Okay, so now you have 3 possible outcomes. And so you're supposed to guess whether your state is 0 or your state is plus. So what do you actually do with the 3 possible outcomes? You need to say, okay, if I get outcome 0, what do I guess? So for each outcome you have to do that. And now that I have 3 outcomes, I can't just say, okay, like 1 corresponds to 0, the other corresponds to plus, because what do I do with the 3rd outcome? What would be a good strategy? What's the 3rd possible thing that I could guess? Or I could say in this challenge?
I don't know.
Yes. Exactly. You can refuse to guess anything. You can say, I don't know which state it is. So a good strategy for this, mix it up. It's okay, so if the outcome is 0, you will guess that the state is plus. If the outcome is 1, guess the state is 0. And if it's 2, guess nothing. It's a good strategy if you don't want any mistakes, you just don't guess anything. So if you just always guess nothing, then these error probabilities, P and Q, of making a wrong guess would be 0. But you also never achieve any correct guess. So let's see how well this strategy performs in guessing what quantum state someone handed to us.
Sorry, why have we gone from 0, 0, 0 plus? Where was that?
Sorry?
Why have we changed from getting a 0 to guess?
You mean, yes. Here I said if the outcome is 0, then we guess is 0. It's because the way I constructed these is different, and I wasn't very consistent in the labels. Because before that, our 0 operator was 0, 0. But now I decided to call it 1, 1, so the role is a bit switched. for the calculations, it's actually very helpful to observe that the second operator, this corresponds to, it has a nicer form in different cases. So, this M1. You remember how the plus minus states were defined? The minus states was exactly 1 over square root 2, 0, minus 1. So what's actually written here is this prefactor. That's minus. That's helpful to make calculations easier. Okay, and now we also want to see how our probabilities look like to make a wrong guess. So we want to calculate P and Q again. So again, the probability that the outcome they have to see if it still fits the limit. So a wrong guess when the state is 0. So we're doing something wrong if the outcome is 0 and we guess that it's a 0 in this case. So I should change the this is where we make an error in this case because now in our strategy when the outcome is a 0 we guess a plus. So if the original state was 0, this is an error. And the way to calculate it is the same. So we have a 0 state, and when the outcome is 0, our measurement operator has M0. So if we use the formula and put that in, we get the prefactor. And then the scalar product of 1 and 0 again. So these are all equal to 0. So this error is equal to 0. Very nice. Now we need to check what happened to the other error. So this is now the probability of the outcome is 1, but the state goes to plus. Okay, so it's the same strategy. Calculating. Now we can use that, we can write this measurement operator M1 in terms of the minus state because the calculation. So you see we have the scalar product of plus and minus, which are also two orthogonal states. So this is also 0. So with this strategy, we actually never make a wrong guess.
I just want to ask, like, when you say outcome 0, like, do you just mean you apply the operator M to the state that you have, or like, what do you?
It means that to calculate the probability, I use the operator M0. The measurement is described by all the operators, but the calculation, calculate the probability of outcome 0, and then plug in the measurement operator corresponds to outcome 0.
Why is it that when you just look at the form of M0, you would say, like, I would guess if outcome is 0, that I would choose to guess that it's plus?
Yes. You could also decide for a different strategy. Like this is a choice that I made, what to guess with which outcome, and I chose this strategy because I know it's the one that works. You can start with a different one, saying when the outcome is 0, I also guess 0, and calculate how well that performs. And then you will see that you always make wrong guesses.
But so in general, you just try all the combinations, see which scheme works best, or is there like a way to just see it naturally from the form of operator?
So there's a way to see what will probably work best, like depending how complicated your operators are. But in this case, you can see it because this is the projector on the one state.
Yeah.
That means if a 0 state comes, it will always like be a 0. So this operator rules out the possibility that it could have been a 0. And the next one, since it's the minus tail, rules out the possibility that it could have been a plus. And in looking at it that way, then you can come up with the fact that this strategy is the one that will work best. Okay, good. So this is a great strategy because we never make a wrong guess. We sometimes have to say, I don't know, because the outcome could also be 2. But if we say we don't know, it's not a wrong guess, it's just not a guess. So to see, and this works particularly well because these measurement operators, instead of trying to figure out which state it is, they check which state it is not. So the first one rules out the 0 state, the second one rules out the plus state. But what is equally important than not making an error is to see, okay, how often do I actually make a conclusive guess? Like, what is the probability that I get one of these outcomes where I can make a guess? Because if in 99.999% of the cases I have to say, I don't know, then it's still not a very useful strategy to guess the quantum state. So we also need to calculate the probability that we get a conclusive outcome, so that the outcome is 0 or 1. So that's the last part. Like, what's the probability of correctly guessing which state is given? So what's the probability of getting a conclusive outcome? So for this one, if we get a conclusive outcome, the state if the state was 0 and the outcome is 1, then we can make a guess. And also, if the state was plus and the outcome is 0, then we can make a correct guess. We need to calculate the probability that this happens. So probability of guessing correctly be like the probability of getting the state 0 in the first place, which I just assume is 50%, so both states are equally likely. And then if the outcome is 1, given that the state was 0, plus other case that the outcome is 0 and the state. These are the two cases where I can actually make a guess. Okay, and then these probabilities we calculate again in the way we have done before. So we have 1/2 times state 0, measurement operator 1, state 0. That's the case where the state is plus and the measurement operator is n0.
Why you multiply the probability by 1/2?
So to get the probability that we're correct, I need to multiply the probability of getting outcome 1, given the state was 0, times the probability that the state 0 is handed to me in the first place. And I just assume it's equally distributed.
Just on that question as well, I don't fully understand why we need to do this conditional probability, because we've just worked out that the, say, given outcome 1, the probability of getting the state plus is 0. In the previous part.
Yes, but in this case, if you have the state 0, the outcome could also be 2.
Okay, yeah.
So
Sure. Thank you.
So, if you plug in the measurement operators for these things with these prefactors, which is the same for both measurements, 0. And 0, so that's the first one. All of these scalar products the square root of 2. So this is 1/2 plus 1/2. So my result 1/2 times this prefactor. Yes.
So maybe it repeats with the question from before, but the 1/2 on the very top, that came from the fact that you're choosing between plus and 0. Like
Yes.
Okay.
That we have this probability correctly. I also need to include what's the probability of having a 0 or a plus in the first place. Just assume it's the same probability for both. If the probability distribution over this is somehow biased, then you just have different weights.
So I'm still a little confused by what's meant by outcome being 0, because the M0, M1, M2, they're just operators, right? So if someone hands me a state, I have a vector in the Hilbert space, and so then how do I decide which outcome is what does it mean that?
Yeah, so like your measurement is this set of outcomes, right? Like the measurement is described by the whole set of outcomes. And when you implement this measurement in the device, you implement all of them, and yeah, the device will output 1, 2, or 0.
Like say if I
and then, like, now I want to make arguments about how the measurement will behave, like what is the probability of getting the individual outcomes, and then I need the individual formulas for the operators. This is something that is a mathematical object that helps me calculate probabilities.
So these measurements are the operators, but the outcomes are 0, 1, and 2, such that if I apply the operators to the vector and then apply the ket on the other side, you would get 0, 1.
Yes, that's what probabilities is. So the fact that this is the way we calculate probabilities for the outcomes, so one row, is like an empirical insight that people have. Like it doesn't have to be this formula, but it's like this matches what we see. Okay, so this is the probability that we make a correct guess, and now we can translate this into like a decimal number to understand how much it actually is, and if you calculate it, 0.293 roughly. So only 30% of the cases you can actually make a guess for what state it is. So in 70% we have to say we don't know anything. So it's not particularly successful. Like you never make an error, but also in 70% of the cases you have to say you don't know very well. And in the course I gave last year, I also gave my students this exercise, and one of them accidentally called this, instead of like it's called unambiguous state discrimination, because you never make an error. And my student accidentally called it unambitious state discrimination. And it fits very well because only in like 30% of the cases you actually make a guess. Found it very fitting. And so like you can't do better if you want to like not make any errors, but so you can investigate, okay, if I allow a certain amount of errors, how well can I do that? And then you can find a trade-off between how many errors are you willing to make and how often would you like to be able to actually make a guess. Okay, are there any questions about this exercise? Yes?
How would you measure up like M2 in the lab?
the question is like, how would I actually implement these measurements? That's a whole different question. But one nice strategy that you can always do is like you don't measure it. Basically, you have two measurement devices. One corresponds to M0, one corresponds to M1. And if there's no click in the detectors, you just assign it to the last outcome. Okay, then let's look at the second exercise.
Then, yes, positive definite, if it's positive semi-definite on a complex Hilbert space, or sorry, any complex vector space, it must be Hermitian.
Okay, thanks.
I'm sorry, and it has to be a complex Hilbert space. In the real Hilbert space, there are counterexamples.
Okay. Okay, in the second exercise, this is a different direction. I mean, here we want to use like quantum states, specifically entangled quantum state, to share secrets. Let me erase this.
So, slightly weaker requirement. The inner product for any two vectors just has to be real. That's the only requirement.
Oh, okay.
But that's not Hermitian.
No. It's just that you want the sandwich VMV to be real for all V in your vector space, and that is sufficient to show that the operator is Hermitian if your vector space is complex.
That depends whether it's infinite dimensional.
I'll discuss it later.
Okay, now we're in a situation where we have three parties, Alice, Bob, and Charlie, and they share an entangled state between the three of them. And they have a secret bit that they would like to share, they would somehow like to access. Let's say Alice really needs to know this bit B, and it's only encoded in this quantum state. This information about the bit B is nowhere else in the world to find, so she can only get it by somehow using this quantum state. I want to figure out how exactly she can access this bit B. Okay, so it's okay, so first, we're in the situation, Alice, Bob, and Charlie, they're in three different parts, let's say, of the world, and somehow they can't meet and just make a measurement of the whole quantum state altogether to get this bit B. So they somehow have to communicate with each other. And let's say the first thing that Alice tries is she has one part of this three-partite state in her home, and she tries some local operations. She sees if she can get this information just from her local state. I want to see how well Alice can do that. When I looked again at the exercise, I realized that one important part that we need for this I actually forgot to introduce in the last lecture, and that is how we get the marginal state of one party from a multipartite state, because we need to argue about Alice's local state in this exercise. And we only talked about, okay, if I have a state of Alice and a state of Bob, how can I get the joint state via the tensor product? But we didn't talk about, if I have the state Alice Bob, how can I get a local state for Alice? And that's via the partial trace. So I just want to define this. So I define it for two parties, but it's easily generalizable for any number of parties. Let's say we have a bipartite state, AB, like a density matrix, the space of density matrices over the space of the Hilbert space for Alice and Bob. And we have a basis for the space B. It's vectors I and B. So it's an orthonormal basis. Okay. Then partial trace over B. Is given by trace over B of the state over AB. And we use this basis and like sandwich it from both sides to the quantum state. So we take a sum over all the basis states and give the identity of the A system tensor the state in the B system and make the same thing on the other side. And often we simply write this as the state sandwiched to row AB, even though the state itself is only unknown. So this is what we'll use to do the exercise mostly. So in the first part, Alice wants to access just her local quantum system and see if she can get information about the bit B from her local system. And to see what information is in her local system, we can take the partial trace over Bob and Charlie and then look at what Alice's local state actually looks like. Okay, so to get but only on Alice. Sorry, it's not necessarily a pure state. Let me just write it like this. So the state on Alice's side, partial trace over Bob, over Bob and Charlie of the tripartite state. And you see the partial trace, it only works for density matrices. There's no partial trace for pure states, so for vectors. So we also have to build the density matrix from the state that we have. That means we have to okay. And then we need to calculate the partial trace of Bob and Charlie of this tripartite state, which means, according to the definition, we need to find an orthonormal basis on the state of Bob and Charlie. And the simplest choice for this would be, since this is in the 0-1 basis, we just take the 0-1 basis for the space of Bob and Charlie. So in this case, the basis would be 0, 0, 1, 1, 0, 1, 1. Everything is on Bob and Charlie. Okay. It means you take this, you write everything out, you get something like so if you write out this state. This. Oops. Okay. And here we can make some observations. And the first one is that, so we would like to find out this bit B. So ideally in Alice's state at the end, somewhere this bit b is still written in this state. The first thing that we can see is that minus 1 to the power of 2b will always be plus 1, because it's 2b. And then when we take the trace over Bob and Charlie, that means, as you can see here from left and from right, it's always the same quantum state that's sandwiched there. That means when we have states like elements like this, where the left and the right side are completely different elements, then no matter which of these states I take, on one side I will always like match a 0 and a 1 in some way. So get the scalar product of two orthogonal states. So those will always be 0. That means these cross terms here will both just be 0. And from these outer terms that are not 0, you see that the terms that survive are when I take like the term that corresponds to the first basis state and I sandwich it with these zeros, and then the last one, and I sandwich it with these ones. Those are the only two terms where I don't get zeros in it. That means, in the end, what's left of it, so now I'm going to take the trace, and get 1/2 to 0, 1/2, 1 for Alice's state. This is all on Alice. Okay, what does this tell me about Alice's ability to guess the bit B? Yeah?
She has no idea. It's an identity.
Is all the elements here where B was somehow involved just cancelled out. So on Alice's side, the B doesn't play any role anymore. She has no way of finding out the bit B just from her local state. In fact, this state here is also called the maximally mixed state. This is like an equal mixture of 0 and 1. And since this is a qubit state, like 0 and 1 for the basis, so this is actually 1/2 of the identity on Alice's side. So this is a state that generally contains no information. Okay, so her local state will not be helpful to get any information about this bit.
Just to make sure I understand, so when you start by looking at both A, B, C's state, like this is just a state, so you're like absolutely certain what it is. But when you take the trace, like you're essentially sort of rolling out what's happening on B and C. So now you have some uncertainty. Is that what's happening?
Yes.
So then
we use the information about what happened in B and C. And in particular, we also lose the information how A was connected to B and C. So this is really just the information that's available only when I have only access to E.
The fact that they're connected in some way, is it because it's like not a pure tensor, or like what?
Yes, because it's an entangled state.
So if it were if it were a non-entangled state, would this?
Let me give a helpful example. So, for example, if I have a state for Alice and Bob, that is simply, let's say, that's like a tensor product, rho A, tensor rho B. Then if I take the trace over B, I just throw away this part, and I have like exactly A. So that means if I so the trace of B over rho AB is exactly the thing that is already in the joint state. But on the other hand, if I have an entangled state, so let's say if I have 0 plus 1, 1, like on AB. If I now take the trace over B, like if you do this calculation, plus AB, we take the trace over this. If we do the calculation, what you will see, like this is 1/2 over the times the identity on Alice's side. And if you do the same thing, like take the trace over Alice of this state, you will see here Bob also gets the identity. That means, on the other hand, if I take the local states and try to use a tensor product to get the original state back, I will not get this state back by taking the tensor product of the two marginal states, in contrast to this case.
So in the second case, it's like A and B together, they know exactly what the state is, but
Yeah.
separately they don't know anything.
Yes.
But isn't that?
We'll
is that
get back
weird?
to that point.
Oh.
Yeah. Yes. So then, like, if you know the locals, both of the local states, that doesn't mean you know the joint state necessarily. Yes, but we will get back to that point. Okay. So yes. So apparently Alice cannot do anything on her own, but maybe like one of her friends can help. So let's say she asks Bob to help, and then there are two parties. Maybe with two people they can actually do something and get information about this secret B. So in the second case, we want to look at, okay, what can Alice and Bob do? So how does the marginal state for Alice and Bob do? Still not considering Charlie. So now I have to look at like row AB. So I have to take the trace over Charlie on the same state here. And then I can do like the same thing as before. Now as a basis I can just choose the 0, 1 basis. The cubic space that I need to trace out. And I can make the same observation as before, like the state in the trace is the same. So you also see in the last part this the dependence on B vanishes because it's to the power of 2B. And also, if I only trace out Charlie, these cross terms will vanish. Because also if I take if I put a 0 from both sides, then here I have a scalar product between 1 and 0, and here I have a scalar product between 1 and 0, so they vanish and we get 0. That means, in case I look at Alice and Bob, what I get is actually also times the identity now on Alice and Bob, but it's still no dependence on the bit B. It's the same situation, and now like even looking at Alice and Bob together doesn't really help. Now you can look at like other pairings, Alice and Charlie, Charlie and Bob, but the situation is highly symmetric, so you will find out that the state for Alice Charlie or Alice or Bob and Charlie has the same form. It's also the identity with no dependence on B. So no two parties, even if they work together, can get any information about this bit B. Yes?
One question. Why do you get the identity over A tensor B? Because I think you'd get.
Oh no, sorry. Yeah, it's not the identity
Yeah.
of A tensor B. You're right. It's this one. Right. So this is the state that you get, but still no dependence on the bit B, because those terms, like, we lost them in the trace. Okay. Yes. So as I already argued for part C, so that the same is true for the other two combinations of parties that could try and attempt to get this bit B. They can also not do anything. It means our only hope is to involve all three parties in this. So one easy way to do is, if all three parties are involved, is they come together, like everybody brings their little qubit and they have the state in one lab, then you can just do a measurement on all three together that reveals this bit B. Okay. But now we're in a situation where Alice, Bob and Charlie, they can't meet for some reason. I don't know, they're very far away, or maybe it's COVID or something, but yeah, we all know situations. So they have to do something where each party acts locally, but in the end, they can still like they can do classic communication, so they can call each other maybe. And they want to come up with a protocol where they each do local measurements on their qubit and then share some classical information so that in the end, someone can figure out what the outcome B is. Okay. And I want to do it in a way that always succeeds. So it's a like deterministic protocol that in the end always spits out the value of B. So I don't know if any one of you has already thought about this question, but does someone have an idea what they could do? Yeah?
I had a Hadamard measure,
What does it do?
which is a projective measurement in the Hadamard basis, which is where we can get a state either plus or minus depending on whether B is 0 or 1.
Mm-hmm. That is correct. I mean, the hint also says what happens if they measure in the Hadamard basis. Let's see what exactly happens if we do something like that. So the idea is that Alice, Bob, and Charlie each measure their like qubit that they have locally in the Hadamard basis. So then we can calculate the probability of getting a certain tuple of outcomes. So let's say Alice's measurement, the output, I call it as A, as B is Bob's output, as C is Charlie's output. So on probability to get a certain triple of output. And we calculate that. So like, as we did before, we take the state we started with, and then we have measurements on the measurement operator that corresponds to the output of Alice, SA, 1 for Bob, and 1 for Charlie. And as I said, they measured in the Hadamard basis, so all these 3 possible outcomes are either plus or minus. Also means that like the possible measurement operators that they can apply are either m plus or m minus. Okay, so here more generally I can say m for the outcome is A. Projector. So outcome is A. So I put this in. I get all these terms for the measurements as A, as B, and as C. This I can rewrite it so that I have the overlap of as A, as B, as C. So this state here is short for the rectangle over 3 states. That means we can look at this overlap between the state for the measurement outcomes and the state we started with, and see what we get for this. plug in the state. So we start with this one. P factor 1 over square root of 2, and then we have two terms in the sum. We have the state and the C, 0, 0, 0. And here's the minus 1 to the power of b. That's where the secret lies. Now remember that SA, SB, and SC are either plus or minus. And the scalar product between plus or minus and 0 is always 1 over square root of 2. That means here we get 1 over square root of 2 to the power of 3, so there are 3 times. But in the second part, so the square root of, the scalar product of plus with 1 is also 1 over square root of 2, but the scalar product of minus with 1, this is minus 1 over square root of 2. So the number of minuses for these outcomes comes into the equation here. So this is actually minus 1 to the power of m, where m is the number of minuses in these outcomes, so 0, 1, 2, or 3, times 1 over 2 to the power of 3 is the number of minus outcomes in SA, SB, SC. Put this together. I get this is 1 plus minus 1 to the power of b plus. Okay. Remember, this is related to the probability of getting a certain outcome. And we see if b plus m is odd, then this will be minus 1, and the whole term will just be 0. And if b plus m is even, we get a non-zero number. That means, so we have two cases. Like the secret b, it's a bit, it can either be 0 or it can be 1. So if b is equal to 0, then this probability then for b plus m to be even, m must be even. That means only an even number of minuses can occur in the outcome. So only tuples of an even number of minus outcomes can occur. And if b is equal to 1, that means m must be odd. For b plus m to be even, that means only tuples with an odd number of minuses. Okay. So from observing how many minus outcomes the three parties observe in their protocol, they can directly infer what b would have had to be. So this is like mutually exclusive. So
Can you repeat why the product of SPAC 0, 0, 0 is equal to 1 over
This is, so these are the plus or minus, those are the two possibilities. And then you have like lots of scalar products here. So this is a bit of a short form to write it, but if I write it out, this is the long form, like this. And if you calculate the scalar product of plus with 0, you get 1 over square root 2, and also the scalar product of minus and 0 is also 1 over square root of 2. So no matter if it's plus or minus, you always get the same number for the scalar product here. Yes?
Like, I just want to know, like, what's the magic? Because you just changed the measurement, the basis of the measurement that you work with, right? But shouldn't, like, reality be somehow coordinate independent? Like, you just change basis and you suddenly have new information. Isn't that strange?
Well, the important part is what's the relation between the basis you're expressing your state in and the basis that you measure it in. If you change basis in like both, then it doesn't matter. But if you change the relation between the bases, then it changes.
It's almost like I have some phase between the...
Okay. Yes, so we see a protocol that then achieves our goal. Alice, Bob, and Charlie measure the respective qubit the Hadamard basis. Then I said, okay, maybe like Alice is the one who really needs access to the secret B. So in that case, Bob and Charlie send their outcomes to Alice. And then together with her own outcome, Alice can like compute M. And then B can just be calculated from M. If I do it this way, even no other party who would listen to this communication can get access to the secret B. Because to get B, you also need Alice's outcome. And if Alice doesn't communicate it, then it's still secret and only Alice has access to it. Okay, so this is how you can share secrets with entangled states. Are there any questions about this part? Yes?
I'm a bit confused. So the experimenters choose an S, right? Each of them?
No, the experiment will give you the S. Like you apply a measurement and it will give you either a plus or a minus as an outcome. You can't influence that.
Okay, then I don't really understand what the measurement is. Like, so you have M plus and M minus.
Yes.
Are
So your
you-
measurement consists of like both operators. And in the implementation, like somehow like both will happen. So I mean the mathematical description of a measurement and the actual practical implementation are two very different things. But the measurement is supposed to take in the quantum state and output either plus or minus.
You can imagine it as instead of like vertical or horizontal polarization, you either measure right circular or left circular.
Yes, but so are these measured sequentially, or am I somehow, like, how should I think of this?
So
You
each
have,
of
like,
them
two
can do it
copies?
there is one state, they all share it. Each of them can do their own measurement independently. They're either going to get left circular or right circular in this instance, for example. And then they just post them to Alice.
But you're measuring M plus and M minus, right?
you know, this is the basis you're going to be doing the measurement. Because I said, like, you can either have vertical, horizontal polarization or like circular left, circular polarization.
Like, you can't calculate which outcome you get with this because it's not a deterministic thing. These operators just help you to calculate what the probability is for each possible outcome. That's why I have an operator for each single outcome. But the measurement is something that implements all of them simultaneously.
So, okay. So am I applying m plus and m minus to this state?
Yes, the measurement does both. And you either get a plus or a minus out of it. But you can't predict which one. This is random, which one you get. You can just calculate what probabilities the two outcomes have.
So here in this case, like you have a scheme where you have 3 people and they need to all like sort of work together to retrieve the information. Can you make one such that you have 5 people, but you only need 3 people, but not less to retrieve the information?
I mean, very easily by just taking exactly this state and having another state for the remaining 2 people in tensor product with it.
Okay.
Then you can do the exact same thing.
Okay, and then you just need to, okay, I see. But then it's like only A, B, and C.
Yes.
So can I say like, oh,
Any A3.
Any 3.
I think you can do something like classically using Shamir's secret sharing, where you have like partial keys.
Yeah. I'm pretty sure there is a way to do that, but I don't exactly know how you would do it. Okay. So these were the exercises I wanted to discuss with you. And then we want to go to continue with the last part of the lecture, where we actually talk about quantum entropies and some more applications. And how long is this slot?
It goes until 7:30.
Yes, and also dinner. So at some point we should make a break.
Do you want to take 15 and then continue?
Yes, so I want to say one more thing, and maybe then is a good time for a break, and then we see how long we see. I don't think we need until 7:30. But I want to show you, like, we want to go to, to talk about quantum entropies and interesting applications of that. And I want to show you a news article a while back about a paper someone wrote, and the news article captures exactly what we want to talk about next. It says this: the scientist knows less than nothing. And that's exactly what we want to investigate in the last part of the lecture. What does it? Why do people say the scientist knows less than nothing? How can that occur?
Like you build this. Sorry, yeah. You build a scheme which determines the probability less than if you just guess. I guess maybe.
No, it's a bit different.
Okay.
Okay, but with this news article, I will let you into the break, and maybe let's continue at 5:45. Okay, and let's continue with the last part of the lecture. Okay, so the third chapter of the lecture.
Yeah.
Quantum entropy.
Did you not wear enough something?
First one we wanted to talk about, like in the classical case, we talked about how can we quantify information using entropies. Now we want to do the same thing in the quantum case. So we start with talking about quantifying quantum information. For that, we need like a quantum version of the entropy that we discussed in the first lecture. So if you remember how the entropy is defined, we decided we don't need fresh air. So the classical entropy, or random variable, is dependent on the probability. And if you see like quantum states as some form of generalization of probabilities, then the formula for the quantum entropy naturally drops out of that. So we define the quantum entropy as follows. So we have a quantum system A. Then the quantum entropy was equal to von Neumann entropy. Of A, depending on the state rho, minus trace rho A log rho A.
Sorry, what is S? Rho A in S of
It's
H?
a set of density matrices on H.
Ah, okay, perfect. Thank you.
And it has a very natural connection to the classical Shannon entropy, because if the state rho, if you know its eigenvalues and like eigenvectors, like you can always write it in terms of its eigenvalues and eigenvectors. So and the quantum entropy is the same as the Shannon entropy for the eigenvalues. The eigenvalues of the quantum state form a probability distribution. So if you have the quantum state in this, it's also called the spectral decomposition, so you write it with the eigenvalues and eigenvectors, then your entropy is simply the same as the classical entropy. So let's investigate a bit in which cases we actually have positive entropy. So where does our uncertainty about quantum systems come from? Maybe here are some examples. Okay, suppose we have a state is 1/2 of 0 plus 1/2 times 1. If we want to calculate the von Neumann entropy, the easiest way is just to get the eigenvalues of this state. What are the eigenvalues of this quantum state?
1/2 and 1/2.
Yeah, for 0, 1, it's already a basis, so this is a variety of the matrix. It's just this. So if I put this into the calculation for the entropy, and then just plug in the numbers and and we have seen this before. This is actually the exact same formula we've seen for a coin flip, where both sides are equally likely. So this will, like, our entropy will be 1. So in the classical case, we said the entropy of a random variable tells us how much we learn on average when seeing a realization of this random variable. So analogously, in the quantum case, this tells us like how much is there still to learn about the quantum system. This is our insecurity about the state of the quantum system. So that means we have some insecurity about what state the quantum system is in. And we can see it in this formula, because what this means is that like the state is the quantum system is either in state 0 or in state 1, and both can happen with 50% probability. And in this way, this means like we don't know what state the quantum system is in, but it is in one of those. So this is like a classical insecurity. But this is different for a superposition. So this is like this one means with 50% probability the system is in state 0. With 50% probability, the system is in state 1. It is different to the superposition of the two. This doesn't mean with some probability the state is in the system is in state 0 and with some probability it's in state 1. The system is exactly in this state. It's just when we measure in the spaces, for example, we get different outcomes with certain probability. But the state of the system is exactly this one. There's no insecurity about the state of the system. So we look at the second example. So if we have a new state, system in state 0, then the corresponding density matrix like this. Now if I want to calculate the entropy of the system, I again need the eigenvalues of this operator. What are the eigenvalues in this case? Yeah?
0, 1.
Yeah, it's 0 and 1. So for entropy, we get 0 times log 0 minus 1 times log 1. So the first term contributes 0. And the second term also contributes 0 because logarithm of 1 is 0. So this thing is 0. So there's no insecurity about the system in this case. show that if I have a pure state, the entropy will always be 0, no matter what state it is. This is 0. Only state of the system. We can quickly prove that. So let's do the torus direction. So we start from the fact like we have an entropy that is 0. So remember we can write the entropy for the quantum state in terms of the eigenvalues of the quantum state. So this is number I log I. Or rho A is the composition of a eigenvectors. And if this entropy is 0, that means each individual term also has to be 0. Because the lambda i's are all positive. And they're all between 0 and 1 because it's a probability distribution. That means they all have the same sign, so no term can cancel another term. So they all individually have to be 0. And we also know that the sum over all these eigenvalues is 1, because it's a probability distribution. And this term lambda times log lambda equals 0, this can only be fulfilled if lambda is either 0 or 1. And if they all have to sum to 1, that means there can be exactly one eigenvalue lambda I star that is equal to 1, and the rest have to be equal to 0. Exactly one. So I star. Which and I star is equal to 1. And the rest is 0. That means a quantum state, like there's exactly one eigenvalue 1. It means in this formula, there's only one term left. This is simply like this for some vector AI. And this is a pure state. So this is exactly the form of a pure state. Means if we have an entropy that's equal to 0, then the underlying state must be pure. In the other direction is even simpler, because if I start from a pure state, it means there's this form for some vector psi. Yeah, that means that the state, if I start from psi and build a basis starting with this vector, then this matrix rho A will be diagonal in that basis with exactly one eigenvalue 1. So this matrix has always one eigenvalues 1 and the rest are 0. And then in that case, we already know our entropy is 0, as in this example. So the entropy directly tells me if I have a pure state or if I have a mixed state. That means all the insecurity I can have about a quantum system comes from like our limit of knowledge that we don't know exactly which of the states the quantum system is actually in. Okay, now in the classical case we had a bunch of entropies that we define, like the joint entropy, the conditional entropy. You can do the same thing, of course, for the quantum entropy. And I want to pick out two that we need. Yeah?
We're getting sunburned. I'm already sunburned. Thank you.
Didn't you put sunscreen?
Everywhere else, even on my head, but I forgot here.
Or to use the time.
Oh.
You need to apply the sunscreen.
Yeah, exactly.
So I'll give you like two entropies that we need to make some interesting observations. So take a bipartite state. So first we'll have a joint quantum. So the density matrix in this bipartite system. Joint quantum entropy. This is very analogous to the classical case, where we just replace the probability distribution with the joint probability distribution. And here we just replace the quantum state with the joint quantum state.
Under script row.
Right?
HAB under script row.
Okay. The more interesting entropy is the conditional entropy. So yes, again we take the bipartite quantum state. Conditional quantum entropy. A given B. So, we define it via take the joint entropy minus the marginal entropy on B. So this formula similarly held also for the classical entropies. You remember we defined the classical version of the conditional entropy via conditional probability distributions. This is not so straightforward in the quantum case because there's not a unique way of defining conditional quantum states. But this analogy, by defining the conditional entropy via the joint and marginal entropy, this one holds. This one. Okay. Okay, so far very analogous to what we did in the classical case. Now I want to investigate what can actually happen with these entropies. Okay, so in the classical entropies, in the classical case, all entropies are positive. Yes?
What do you mean with entropy of B in state rho? Because rho is now bipartite.
Yes. So this is evaluated over the state. We take the partial trace over A, and then we get the state. So over rho B. And it makes sense that entropies are positive because they quantify our knowledge about something. Or the way I phrased it here, they quantify how insecure we are about something, which means if the entropy is 0, then we know everything. if the entropy is positive, then there's still something we don't know about this quantum system. So negative entropies don't really make any sense, neither in the classical nor the quantum. So let's investigate what numbers come out. So for the entropy of like just the standard von Neumann entropy, or even also like no matter how many systems I put in there, I can show that this entropy is always positive. Non-negative. We can also show that for separable states, the conditional entropy is always positive. So we have a combination of product states. The interesting things begin when we don't look at separable states but go to entangled states. So what about entangled states? For example, let's take this state. 0, 0 plus 1, 1. So let's calculate the conditional entropy for the entangled state. That means we have to calculate two entropies, the joint one and the marginal one of B. Joint entropy. What's the value of the joint entropy for this quantum state? Zero, yes. Exactly. Because why is it 0?
This is a pure state.
Yes, exactly. We showed that for a pure state the entropy is always 0. I mean, we showed it for the entropy of a single system, but this just translates to the entropy of multiple systems. If it's in a pure state, this is 0. Marginal entropy for system B, and for that we first need the marginal quantum state on system B. So we need to see what is B. So we trace out A of this state. So again we need to find basis on A. And use the formula we had before. And since our state is a combination of zeros and ones, it makes sense to just take the 0, 1 basis again and do the calculation. So that means if you write out all these terms, or the trace and the state, you have a long sum of states. So for the trace, you need to sum over all the elements of the basis. So we have the zero state on system B. Then here we have the state that's inside the trace. This has a lot of combinations, so this is always on A and B. Okay. Write them all. On the other side, we also have the sandwich with the state, the basis state from the trace. And we have the same term for the other basis state on B. The state inside is the same, except this. Okay, maybe I don't know. Okay, that means we have a lot of scalar products on the system B, coming from the states and the states in system B. If you look closely at it, let me just write out the first terms. So if you look precisely at what's happening, what we have here, like this is a short form for the identity on system A, and then this state on system B. And here for the first term, this is the tensor product of 0, 0, 0, 0 on system A, 0 on system B. And then the bras. And then I sandwich it from the other side. This. Like this, that would be everything that corresponds to the first term in this. And the second one, from the outside, same. And then here we take the next state. And here we have the ones. So those are the first two terms, and then the rest of the 6 terms also come, but I will not write out everything. So now I always combine everything on system A together and everything on system B. You will see that on system A, like you just have the identity on the outside, which does nothing, and then you have a cat A and a bra A. That means on system A, you have simply this object. I calculated the trace over B and not over A. So I wanted to calculate the trace over A, which means I need to get basis over system A and not over system B. So this is also supposed to be on system A. That means in here, like the roles are switched. We have something that acts on system A and something that does nothing on system B. don't have anything on A. But what we get on A, if we combine these things, is always like a scalar product between two vectors. Like this 0 with this 0, and this 0 with this 0. So in system A, we have these two scalar products. And in system B, we get like the identity and then these two objects which give us this. And for the next one, we get 0, 0, and what have I done here? 1 and a 0. Tensor 0, 1 on B, plus all other terms. So you see, for the first one, we have only scalar products of 0 with itself. So this is equal to 1. Here we have a scalar product of 1 with 0, so this is 0. Means the second term vanishes. And if you look at the combinations that we have here, so every time a 0 meets a 1, either from the left-hand side or from the right-hand side, we get a 0 term. From here, in the second part, if a 1 meets a 0 from either side, the term vanishes. That means in the first part, like everything that contains a 1 will go. And in the second part, everything that contains a 0 will go. So in the end, we're only left with to 1. Now if we put this together to get the condition entropy of A given B, which is the joint entropy minus the marginal entropy, so 0 minus 1, we actually get minus 1. So we get a negative entropy if we put an entangled state in at the beginning. Okay, so what does this mean? When we interpret the entropy as, like this is our insecurity about the system. So if the entropy is 0, we know everything about it. So if the entropy is minus 1, like what does this mean? How can you know more about a system than everything? And this is, like the article I showed you before phrased it a bit differently because they use a different interpretation of the entropy that is actually wrong. And says then the scientist knows less than nothing, but in fact the scientist knows more than everything. This is something that like people are very confused about, not only in terms of entropies, but even when like quantum mechanics started to be developed. Like, this is something that already Schrödinger wrote about. He didn't talk about entropies, but he also observed that like it's a difference between observing the state of the joint system and observing the individual states of a system. So what he wrote in one of his papers was, I would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical line of thought. So these type of things that can happen in quantum, for Schrödinger, they were the one thing that really distinguishes classical and quantum theories. And I mean, this is also what we observe, that the classical entropies, they're always positive, which makes sense with those interpretations. In the quantum case, we see they can be negative. And so maybe our interpretation of the quantum entropy is too close to what we derived in classical mechanics. And quantum systems are just it's very hard to get an intuition for them, because all our intuition comes from classical systems, because that's all that we can observe in nature. Like the world that we have access to in daily life is a classical world, so it's hard to get a quantum intuition. But of course, people were trying to figure out, okay, what does this mean? How can I interpret this? And what people in quantum information theory like to do is think about tasks that they can do, think about operational interpretation. So if the entropy is negative, what does it enable me to do? Okay, and this is the last part that I want to discuss, namely a task, like an application of all of this, where we can find a way to interpret this in terms of a task that we can do. Okay. I'll make some space here. Second subchapter of this is application for quantum teleportation. Okay, before we can discuss this application, we need a few more mathematical objects that we need for this. One of them are the Pauli operators. So Pauli operators, together with the identity, form a basis on the space of operators on C2. And you can very neatly also write them in terms of these cats and bras that we have. So the X operator can be written like this. And if you write it as a matrix, it simply looks like this. If you apply it to the states of the computational basis and apply this operator to 0, you can see if I put a 0 from the right side in the second term, I get a 1, because this, I just wrote that. So what I get are the following terms. So here we have a scalar product between 1 and 0. This is equal to 0. We have a scalar product between 0 and 0, so this is equal to 1. In the end, you get out the 1 state. It's the same if you apply it to 1. You get out a 0. So it just flips the state. So that was called a bit flip operator. The second Pauli operator is y. This is minus I times 0, 1 plus I times 1, 0. So the matrix on this side. And if you apply it to the 0 state, you do the calculation with I times 1. If you apply it to 1, you get minus I times 6. And the last one is the Z operator, which is 0, 0 minus 1, is 1, 0, 0, minus 1. And if I apply it to the 0 and the 1 state, for the 0 state, I just get the 0 state back. For the 1 state, I get minus the 1 state. So you see 0 and 1 are the eigenstates of the Z operator. That's also why I called, at some point in the beginning, this basis the Z basis, because they are eigenstates of the Z operator. And together with the identity, this is a basis for the operators on C2. One property that we need is, like, if you square these operators, you get the identity. Operators, because for our application of quantum teleportation we need to work in a particular basis for 2 qubits, which is called the Bell basis. This basis for the 2-qubit case. One basis state is the one that I've already used in several examples. That is this phi plus state. 0, 0, plus 1, 1. Now we can construct the other basis states by starting from this state and just applying Pauli operators to it. That's 1 equal phi minus. I get by doing nothing on system A, but applying the Z operator on system B. If you, on the state that I started. If you do that, if you write this out, you can see what happens is, so on A nothing happens, and then on system B, I apply the Z operator. And according to what we've written up there, that means, like in the first term, nothing happens, but in the second term, we get a minus 1 instead of a plus 1. So the state that we get here is 0, 0, minus 1. Okay. And then we can also use the other Pauli operators to get other states. So then we have plus, which I get from applying the X operator on system B. And we saw the X operator just flips the bit. So both bits on system B will be flipped. That means the resulting state that we get is 0, 1 plus 1, 0. And then we want the last state of our basis, so minus. This is the Y operator. And we use not only Y, but minus I times Y. So if we apply Y to the 0 state, then it flips the bit and also adds an I. But the I is counteracted with this minus I prefactor that we have. So when we get in the first term, it will just be a flip of box bit. This is just the one. And for the second one, the Y will flip the bit and also add a minus I. So what we get is a minus 1. These are 4 states that form a basis of the 2-qubit space. And the important thing that we see via this construction with the Pauli operators, I mean, I could have also just written down the states and told you this is the basis we work in, but it's important to see that all 4 different states are related by an operation only on the B system. So we don't need to act both on A and B, but only locally on B to get to all 4 basis states. Observation is that since this is a basis on the 2-qubit space, it means I can also use it to construct a measurement on the 2-qubit space simply by constructing the measurement operators from these basis states. Basis. Means I have these 4 operators. And I will index them 4 operators, so I can index them with 2 bits. 0, 0, 0, 1, 1, 0, 1, 1. In the first one I will take the first state, 0, 5 plus. Second one is then the 5 minus. And you see the pattern. Then I take psi plus and psi minus. Okay, so now we can go to the quantum teleportation protocol and see what that is about. So the situation is the following. Alice has a quantum system in her lab. So the state, call it psi on system A prime. And then call it phi. And she would like to send it to Bob. But she doesn't have a quantum channel. So she doesn't have a channel where she can just send the quantum system to Bob. She does have a classical channel, so Alice and Bob can communicate classical information. But you can't just send the state. That would be too easy. The goal is Alice wants to transmit the qubit state that she has to Bob. Okay, so if they have this setup where they only share this classical communication channel, is there a way that Alice can achieve this goal?
Yes, the answer is yes, affirmative. We have the additional information from the entropy. You apply, I don't remember the exact sequence.
I mean, at this point, I only have the classical information, nothing else.
Then this would be destructive.
So I only have the classical information. there's no way to do this. I mean, if Alice had many copies of her quantum state, then she could do something that's called quantum state tomography, where she measures she measures the state many times. You remember, like the general form of the qubit state was this. And we also know that the probability of getting a zero outcome and measuring in the spaces was directly given by alpha and similar for the one outcome. So what she could do, she has many of the states, just do a lot of measurements in the spaces and collect the statistics. But to get it exactly right, she would need infinitely many copies of the state. And also with this, like, she doesn't get the relative phase between alpha and beta. Okay, so, but in our situation anyway, Alice has only one copy. So she can't do it at all. She only has one copy that she wants to give to Bob. Okay, so if she only has this, then there's no way to get this state to Bob just via classic. She needs more resources. And the resource that we will give to Alice and Bob is an entangled state, a bell state. So we say there's some magical source that at some point has distributed this bell state to Alice and Bob. Alice and Bob can use this additional resource to help get this quantum state over to Bob. And so what I claim they should do, so first, is that Alice takes the state that she would like to send and her part of this shared entangled state, and she does a bell measurement, so measurement in the spaces on the two states. So, qubit fine and her part of this entangled state. So this is one qubit, this is also one qubit because she only takes her qubit. So it's a 2-qubit system. That means she can do this bell measurement on the 2-qubit system. So she measures the 2 qubits in the bell basis. Which will produce an outcome. So here I labeled them with 2 bits. So that means the outcome will be one of the 4 possibilities. So the outcome is 2 bits in this case.
You mentioned the qubit that she has.
Mm-hmm.
How do you how do you make that like act on
I mean, to apply this Bell measurement to a quantum system, we just need a 2-qubit system. So physically, Alice has this qubit, and she has like one of these qubits. This is a 2-qubit state. So she just takes the 2 qubits and performs the measurement.
Okay. Like it doesn't. Like for example, the first qubit that she has lives in the Hilbert space like HA, and the second one that she has lives in like HA tensor HB, where she only has.
Yeah, but she can take. So, I mean, physically, this would be 2 qubits or 2 quantum systems, and she can just take one of them. So she can just act on one part of the joint Hilbert space.
I see. So in this case, she's viewing it as the Bell basis would be like a basis for HA tensor HA.
Yes, like HA prime tensor HA.
Yeah.
This is where the Bell basis would be constructed for. Yes. Okay, why is this good? Like, what do we win when Alice does this? For this, we need to investigate what Bob's state looks like. So Bob has access to the second part of the qubit, so the second half of this entangled state, and we can calculate how his state looks like after Alice has done this Bell measurement on her part. Okay, for this we need to calculate the post-measurement state after Alice has done this measurement. So suppose the outcome was 0, 0. Calculate the post-measurement state. You take the operator corresponding to 0, 0. This acts on A prime and A. And on Bob's system, nothing happened. Bob hasn't done anything. Apply this to all the systems involved. So prime on A prime, and then phi plus on A B. So to properly calculate the post-measurement state, we also would need to like renormalize it in the end to divide it by the probability that this happens. But I will leave it out for now to make it not more complicated. Yeah?
What is M00 A prime A?
It's this measurement operator in the Bell basis, like specified that it acts on the systems A prime and A, and not A.
Oh.
Because now we have 3 systems, we need to say on which 2-qubit system it actually acts. And when Alice applies it to the systems available to her, then that is A prime and A. Okay. So that means if you write this out, what would we get? The measurement operator is built also by this phi plus state. Okay. And then we have prime and so now you have to like put in all of the quantum states involved and calculate things. Like you can see, you will get some scalar products again, like very similar to the previous calculations. So let me write out a few steps. And this for now. So we'll first put in the states on the right hand side. So the state on A prime and the state on AB. Then this state on A prime, we don't know which state it is. It's the one that Alice wants to send to Bob. But the general form of a qubit state that we know. So this is some alpha times 0 plus beta times 1 on system A prime. in the phi plus state we have defined over there, so it's 1 over square root 2 on 0, 0 on AB plus 1, 1 on B. Now, I've inserted this. Now I insert this part of the measurement thing. I'll leave the first one still as it is. So, I get this states on A. Okay. And here I rewrite this as like a state on all three systems and put together all the different combinations. Square root 2. We have alpha. So here we have a sum of two things, and here we have a sum of two things. So in total we will get 4 terms on A prime A B. And from this you can see like what scalar products will happen and which terms will survive. So we have this 0, 0 on A prime A. So this scalar product only gives a non-zero element if on this side in A prime and A there's also a 0, 0 term. And this is only the case for this. So the other for the other terms there's at least one in either A prime or in A. So only the underlined combination of terms will survive the scalar product. And for the second term, this 1, 1, the same argument holds, so it only gives a non-zero element if it matches the 1, 1 on the right hand side. Okay. So if we do this, then what I get, the only non-zero terms at the scalar product of 0, 0, 0, 0 on A prime A. And in that case, system B is in state 0. And for the second one, 1, 1, 1, 1. In that case, system B is in state 1. So this is always 1. So we get some factor state on A prime A, and then on B we get 0 plus delta times 1. This is exactly the same state that Alice has started with in the beginning. So this is like alpha times 0 plus beta times 1 is the state that Alice had. So this is now exactly the state phi that Alice started with is now in the quantum system of B. By just Alice measuring things locally on her sides, she somehow teleported this quantum state without sending any quantum states to him, just by using this entangled state as a resource.
Is there a reason we used like phi plus AB
As a resource?
Yeah, like could we have used a different one of
You
these?
could use any of these.
On the same
So
thing.
it doesn't matter. This one. Okay, so if the outcome of Alice's measurement is 0, 0, then Bob already has exactly the state Alice wanted to send. But of course, this doesn't always happen. Like each of these outcomes is equally likely. So each of these outcomes will appear with probability 1/4. So if only, like in 25% of the cases, the state could be sent to Bob, this is a bit disappointing because then Alice would lose a lot of states that she wanted to send to Bob. But in the other cases, we can see what happens, and if Bob can do something with that. So far, we also only didn't need to send any classical information yet. So Alice and Bob actually didn't need to use the classical channel yet. So for example, if we get the second outcome, 0, 1, then we can see if we look at this calculation, then if the outcome was 0, 1, we get Bob's post-measurement state, we have to take a different measurement operator, one corresponding to 0, 1. And this applied again to the same states as before. Now we can use the relation that we found before between these Bell states. So if I write down the operators for this measurement, these are the phi minus operators on A prime and A. And we know that phi minus is related to phi plus just via the Z operator. That means I can rewrite this to phi minus here. This state here I can rewrite as phi plus, where I have applied the Z operator to the second system, so to A. And then if you do this calculation again, which I will not do again on the board, then what you find in the end, what Bob's state is, you see, this states, then Bob's state is the Z operator on the system B applied to the state phi B, the one that Alice wanted to send. So Bob doesn't get exactly the state that Alice intended to send, but it's the state together with an operator. So there needs to be some additional step in the protocol to correct for that. we like do the same manipulation for the other two possible outcomes, you can see a similar pattern. So the remaining outcome we have 1, 0. Then Bob's state would be x applied to the state phi, and if we have 1, 1, and this is minus I y applied to the state phi. Okay, so like exactly these operators that appear in the relation between the balanced states. Okay. But these operations are something that if Bob knows that his state is of this form, he can just apply an operator to it and reverse this. Because we also saw, or I told you, that the operators like square to the identity. So if Bob knows that this is his state, he can just apply an X operator to it and get the original state back that Alice wanted to send. He only needs the information that his state is in this form. And this is exactly the outcome that Alice has, so the 2 bits that Alice got as an outcome. So we need, so Bob knows Alice's outcome. Then he knows what state his system is in. And he can apply an operator to correct this twisted state and get the original state back. The state xb applied to phi, then he just applies xb on his side, and he gets just the state. So this quantum teleportation protocol requires one more step. It's not just Alice makes a measurement and Bob then has already the state, but also Alice needs to send him the outcome. So these 2 bits of classical communication she needs to send, so Bob can apply the corresponding correction operator. Performs the corrections. So what this protocol in the end requires is 2 bits of classical communication and 1 entangled state as a resolve. So communication is 2 bits, and the resource is 1. And you can see the name quantum teleportation comes because you can send an arbitrary qubit state without communicating quantum information. So you don't need to actually send a quantum state, you only need to send classical information. Of course, you still need to have as a resource an entangled state, but the nice thing is this entangled state you can create at some point where it's convenient for you. You can create like a repertoire of many entangled states that in the future you can use for sending quantum states when you need it. Of course, you need a quantum memory for that and everything. The point is you don't have to send the quantum state itself over a quantum channel. Okay, and this is, like if you connect it back to the negative entropy that I still have here in the corner, then you can think about it as this entropy is only negative if there is entanglement between Alice and Bob. So negative entropy means that Alice and Bob share a resource that can be used for future quantum communication. So it means that it's not that Alice, they know more than everything about the quantum system, it's more that the quantum system has the potential for future quantum communication. That's like one way of interpreting this entropy. That it tells you, okay, there is a resource that can be used for communication in the future. It's not as satisfying as other interpretations of this entropy in terms of how much do we know about the system. But I think this also comes from the fact that we don't have any good intuition about quantum systems in the first place, because we're very classical beings, and our intuition comes from classical systems. But it's nice to connect it with these, like, with a task that tells you, okay, your entropy is negative, then you can actually perform this kind of task. Okay. And with this, I'm at the end of everything I want to tell you about quantum information, and I'm happy to answer any of your remaining questions.